So in the last video, we talked about making a scatter plot, and that's all great. It's important, obviously, to visualize data, but it's more important to be able to do something with it and to use that data to draw conclusions and make predictions about other events using the data that we've been given. That's the whole reason we study statistics. And that's what we're going to talk about here, is actually using our scatter plot and doing something with it. And we're going to do this with a line of best fit, and sometimes it's called the linear regression line or least squares regression line, although that last one's not as common. And when we're talking specifically about linear regression, we're going to use this to display the trend of a scatter plot and make predictions about other elements not represented on the graph. Right? This should say just predict. Right? So if I have, maybe here's like my random scatter plot with a vaguely positive trend, my line of best fit is going to find some way to estimate, approximately what does this trend look like. And we can actually use this equation. This will actually give us an equation, a linear function that we can use to make these predictions. And just like any function, any set of data, we have a domain and range. So of course, if you remember from algebra, the domain of a scatter plot is the finite set of x values plotted on the graph, and the range is the y values, just the list of x and y values. We're going to use this domain to understand if we're interpolating or extrapolating data. So interpolation or interpolating data is to predict a y value given an x value within the span of the scatter plot's domain. So if my data, maybe if my data is just like 10, 40, 60, 75, right? And I'm asked to predict for like 35, right? Well, this 35 fits in the span of my x values. So we would call that interpolation. Well, its opposite is extrapolation, and to extrapolate data is to predict a y value given an x value outside the span of the scatterplot's domain. So in this case, if I were to give you like 82, well, that falls outside of my data set here. And so this would be extrapolation. I always like to think about the difference between introverted, somebody who is introverted, and somebody who is extroverted. Right? It's the same prefix. Intro, inter, within, extra, extro, outside. So extroverted, outgoing, extrapolate, outside the span of the given data. So we're going to go back to the example that we've been working on over and over again. And just to kind of explain what we're talking about with my domain and range, my domain is just the set of all of the data points, right? So I would just go ahead and list out all of my x's. I'm not going to do it, but you get the idea. And my range, I would do the same thing, right? I would say 102, 133, and so on. Again, I'm not going to do it, but you get the idea. So we're going to go back to the set of data that we've had before. We're going to determine the equation of the linear regression line and then actually use it to predict expected sales when the temperature is 88 degrees. So that's exactly what we're going to do here. Actually, let me quit out of this window. I don't need it. Let me clear all of this. So let's just make sure I have the right data entered in again. And I do, which is great. So as before, we were able to, is my stat plot on? No, it is not. As before, we were able to view my scatter plot. All right, so you can go back to the first video to review how to do that. But I want to take this and actually determine the equation of the linear regression line. So to do that, I'm going to press stat. Right? If you remember, we used edit to enter my data. But this time I'm going to go to calc, and I'm dealing with linear regression. And actually, if you look through, you see I have two options. We're always going to stick with number 4 because we're used to seeing linear equations written in this ax plus b, right? Except instead of an a, we traditionally use m for slope, but it means the same thing. So we're going to use number 4. Enter. This x list and y list is just asking me to tell the calculator where I stored my domain and range, and I put them right in L1 and L2, so we're good. There was no frequency list. I'm not going to show you the store yet. We're just going to press calculate, and you see I get my A and my B. So pretty easy, right? And then if I ask you to write down the equation of the linear regression line, you're just going to give me, with some rounding, right, 4.44x minus 187.67. Right, so you would just plug the A and B exactly where they belong. We'll come back to what this R means later. Now, if you wanted to put this on the scatter plot, I would never ask you to do this because it's not a step I can actually check. But if you ever wanted to see what it looks like, if you go back to Stat and Calc, you hit 4, and we go down to the store regression equation, I can actually put it right into y1. And I'm going to do that by pressing vars and go to yvars and function and then y1, or any of the y's I guess is fine. So that way if I can calculate and then I can graph it, and you can see that the linear regression equation cuts right through the data and tries to get this line as close to all of the points as possible. But again, I'm not going to ask you to do anything with the scatterplot display on your calculator just because I can't correct or grade that portion. So all you really need to know is stat calc 4, calculate, plug in where appropriate, and then that's all she wrote. So we've got our linear regression equation now, and so let's do something with it. I want to know how many water bottles we can expect to sell when the temperature is 88 degrees. Well, all right, this seems important, and the equation I came up with seems important because that is our model, right? We're going to use our model to make these predictions. Well, so if I'm going to use this temperature in some way, I just need to know what our variables mean, and just from the way that I've entered things in, we've kind of defined x to stand for the temperature and y to stand for the sales. So if I'm given the temperature, I'm just going to go ahead and plug my temperature in for x. So I've got 4.44 times 88 minus 187.67. And that gives me, well, it actually gives me 203.05, but that doesn't make sense, right? I can't sell 0.05 of a water bottle. So we're just going to round this down to 203 water bottles. And if you remember what our scatter plot looked like, this is a good representation of the data because that line fell pretty close to all of the data points. And we're going to talk about what that means in a little more detail in a minute. By the way, because I almost forgot to do it, with my part 3 here, this would be an example of interpolation. Why is it an example of interpolation? Well, that's because if I look at my range, right, my x values range from 65 to 100. Right, and 88 falls within that range, or within that span. I don't want to use range because we use range for something else in math, right? So within that span, so that would make it interpolation. Right? If I gave you like 50 or 110, well, that falls outside of the range, the span, and that would be extrapolation. But in this case, it's interpolation because it falls inside my domain. So again, here's actually your, right here is actually your linear regression line. Again, you can see how nice and clear and clean that is, and right around all of the data points. So let's talk a little bit more then about how we can actually tell how well a model fits the data. And that's done through something called correlation, which we talked about a little bit earlier, but now we're going to talk about putting a number on it. So we have this thing called the correlation coefficient, and we give it the letter R, and my guess is we get the letter R from the word regression. Well, R is a number between -1 and 1 inclusive, and we can use this to gauge how well a linear model fits the data. And R tells us both the strength and the direction of the line of best fit, right? So I have two parts. I have strength, and that's going to be one of these very weak, moderate, strong. And I also have direction, and that's going to be just positive or negative. So I'm going to use this as a tool here, right? Basically, every 0.25 that you go in either direction, you move a level, right? So when from 0 to 0.25, I've got very weak, and then I've got weak, and then moderate, and then strong. Basically, every 0.25 you move, same thing over here. we go up kind of a level of strength, so to speak. And all I'm going to do is match my number onto this scale. So if I have like 0.452, well, that's going to fall somewhere in this category, right about here. And that's a positive number, so that would be weak positive correlation. Versus if I have something like negative 0.897, well, that's going to fall maybe about here. And that's going to be strong negative correlation. So just to kind of give us a sense of what this looks like, a 1 or a negative 1 gives me exactly linear data, just either in a positive or negative direction. Right? It's perfectly linear. The line lines up on the points exactly. And then, of course, if you get to 0, there's really no rhyme or reason to the way the numbers are being placed. You really can't come up with a correlation at all. Right? So we want to know how linear does this look? And that's what we're doing with correlation. Well, you can't really do this by hand, so we're going to do this on our calculator, and it's actually really easy because it just gives it right to you. Yeah, so as I said, this gives it right to you on your calculator. All you're going to do is stat calc 4, just like we did before, and go right down to calculate, press enter, and there it is, right here. There's my R. Because we're dealing with a linear regression, we don't have to worry about R squared. R squared is more important for nonlinear regressions. So we're not going to worry about that. We're just going to look at my last line here, R. Now, for some of you, if you haven't done anything like this before, R and R squared will not show up right away. So to turn this on, it's a little bit of a pain, but we're going to go to second and then catalog, which is the 0 key. And we need to go all the way down to something called diagnostic on. So to save some time, you can see that my alpha lock has been turned on, so I can actually just click the D for diagnostic and scroll down until, there it is, diagnostic on. I'm going to press enter. I'm going to press enter. It's going to say done. And then I'm going to rerun my linear regression, and it's going to give me my R and R squared. Right? I already had mine turned on because I was practicing with this before and I didn't shut it off. But if you reset your calculator, or if you haven't done this before, originally all you'll see is the A and the B. So you have to turn your diagnostic on in order to do that. So again, that's just second catalog, and you're going to work your way down until you see that diagnostic on. And that's all you need to do to find the correlation coefficient. And paying attention to my rounding, 3 decimal places gives me a correlation coefficient of 0.972. I want to interpret what this means. So I want to give my strength and my direction. So strength is going to tell me kind of which of those 4 categories, right, which of these 4 categories does it belong in. And 0.972, that's pretty darn close to positive 1, right? So it's super close to 1, and that's going to tell me that it's strong correlation. And it's also a positive number, so this is going to be strong positive correlation. So is the model that we calculated earlier a good fit for the data? Yes, it is, because it's a strong correlation, and the strong correlation is what makes it a good fit for the data. Right? The closer it is to 1 or negative 1, the better a fit for the data it is. So this is a really good fit for the data that I've come up with here.